How do I unmute? Huh?
Okay, okay. Now I hear you. Now I hear you. Yeah.
Okay. Oh, yeah, I see. Okay. Yeah, right. So, sorry, this tab can, but I think we can still do it better, right? Ah, okay.
Want to see the speaker?
The second icon comes there. Second icon can come up.
No, no, not that.
Yeah, okay. Okay, hold on. Yeah.
Okay. Yeah. Okay, I should start now. Okay. Okay, thank you for the introduction and good morning to everybody. I would have loved to be there in person, but unfortunately something came up, so I could not. Maybe next time. So let me start with the presentation. So this talk is about this problem called POSLP and some of its variants, which we study in this paper. So the first two sections, I'll basically do like a very brief survey of the problem and what is known about it. And in the last two sections, I will tell you a bit about what we do in this paper. Okay. So first, let me start with a very broad kind of problem which we study in this paper. So the kind of problem which we study in this paper, that we are given integer capital N, and that we want to decide whether this integer is 0 or positive, right? So of course, the integer is not given in the usual bit string representation, because then the problem is trivial. So we are given some implicit expression to compute this integer n. For instance, like you might take this example. So let's suppose I have four integers a, b, c, and small n, and you can define this new integer now, and you might want to decide whether this integer is 0 or not, right? So, and essentially, if you want to decide 0, well, if you want to decide this capital N is 0 or not, this is a, like, you can think of it as a computational case or computational analog of the Fermat's last theorem, right? And you might also want to decide whether this is a special case of this is a very special case of positive P, and you might want to decide whether this capital N is positive or negative, right? And so to formally define the problem positive P, I need to briefly introduce this notion of arithmetic circuits and straight line programs. And so an arithmetic circuit is nothing but a arithmetic or algebraic analog of the usual notion of Boolean circuit. So it's a directed acyclic graph, and at the inputs or at the leaves, and the bottom layer we have the constants 0, 1, or variables x1 to xn, right? And every gate in the middle is either addition, subtraction, or multiplication, right? So in particular, like in the usual literature, the constants
Gaurav, you are not audible.
um, now, is it good now?
Yeah, yeah, but the screen is not shared anymore.
Okay.
So what are the hyperproperties? So hyperproperties had been, some hyperproperties had existed since many decades, but in the first decade of the century, Clarkson and Schneider coined the term hyperproperties, meaning the following. So when you have a
Just from this slide.
Okay, good. Okay, yeah. So in this talk, we are which are constant free, in the sense that the only constant which we allow are 0 and 1, right? And all the other constant which you need to use in the circuit, they need to be computed starting from 0 and 1. And yeah, so naturally, every such arithmetic circuit computes a polynomial, an integer polynomial. And the size of the circuit is basically the number of nodes in it. Right, a state line program and arithmetic circuits are used quite interchangeably in the literature, but state line program is nothing but a sequence of instructions, like on how to evaluate a given arithmetic circuit, right? So there might be many ways to evaluate the nodes of an arithmetic circuit. If I tell you like, okay, you should evaluate this node first and then this node second and so on, that is what is called a straight line program, right? And in this talk, basically, I will not distinguish them too much. I will just use them interchangeably. Right. So a small example of a arithmetic circuit or a straight line program. So we have this circuit and this circuit computes this polynomial, right? So the first subtraction gate computes this x1 minus 1, and the multiplication gate computes x2 times x3, and the top gate computes the addition of both these polynomials. Right. So now let me come to the crux of the paper, the central theme of the paper, the problem Poisson LP. And suppose now if I'm given as input a straight line program P, which does not have any variables, right? So that will compute an integer. It does not have any variables, so the object which is computed will be an integer. And the problem poses will be basically asked that I give you a straight line program P, and you tell me whether the integer which is computed by this straight line program P is positive, right? So, and you can even get a very, you can see that this straight line program P is a sequence like this. It's a sequence of L plus 1 many integers. The first integer is 1. And then all the subsequent integers are computed by applying some arithmetic operation on, applying arithmetic operation on two previously computed integers, right? So the ith integer will be some either addition, subtraction, or multiplication of two previously computed integers, right? The integer which we compute at the end, the last integer BL, we say that this SLPP computes this integer BL, and we say the size of this P is L. So number of integers, or approximately that.